Introduce our today's expert, industry expert actually. So, Lakshya Priyadarshi is a technology leader in the field of quantum computing and currently serves as the Vice President of Quantum Platforms and Solutions at QPI. In this role, he drives the strategy, development, and deployment of quantum and quantum-inspired solutions designed to solve large-scale industrial and enterprise optimization challenges. His works focuses on integrating AI, advanced optimization, and emerging quantum technology to create high-impact production-ready systems for domains such as logistics, supply chain, and intelligent automation. Lakshya brings a strong technical foundation in quantum software engineering, including expertise in noisy quantum circuit simulation, variational quantum algorithms, and hybrid quantum classical frameworks. Earlier in his career, he worked as principal engineer and held senior technical positions where he built simulation tools, contributing to algorithm research and collaborated on applications of quantum computing for real-world use cases. He also published technical work on noise modeling, optimization using quantum approaches, and density matrix-based simulation techniques. Passionate about bridging academic research with industry needs, Lakshya actively works toward accelerating the adoption of quantum technology by making them accessible, scalable, and aligned with the business value creation. So, with his combined expertise across quantum computing, AI-driven optimization, and enterprise technology ecosystem, he is recognized as a leading voice in shaping the practical future of quantum-enabled digital transformation. So, we are very much privileged, sir, for your presence in our today's session. So, on the behalf of all the participants as well as the organizing committee, I welcome you to the session, sir. Over to you, sir.
Yeah, just to add one or two points, as he has developed, one of the developers in IISc, he did his internship. During that time, he developed the quantum simulator QSIM. So some of you have been introduced to QSIM this time, and we did some experiments on that. So he was one of the person who was part of the team which developed it. At that time, he was an engineering college intern working with IISc Bengaluru. So within a very short period of time, he is a leading voice on quantum computing. That's what I would like to say. When I visited QPI, he showed me the live quantum computer. So the first time I could see, and it was a very different experience for me. And looking at him, he's a role model for many youngsters. Within a career span of less than 6 years, he has reached what he is today. So I think his journey also, I hope he will share a few points of what how he picked up things and how he has moved forward. And over to Dr. Mr. Lakshya Priyadarshi, a very young and dynamic, I would say, vice president of a big company. They are part of the first Make in India quantum computer, QPIAI, the 25 qubit quantum computer. So he is one of the developers in that case also. Over to you, sir. We'll be very happy to listen to you. Thank you.
Hello, hi everyone. Very good afternoon to you. Thank you, Dr. Pilli and Dr. Vikash. Really kind introduction. So, with that, let me begin this session about the industry viewpoint in quantum computing and how we as an industry are putting in our efforts to develop the scalable technologies around quantum computing. Our efforts into indigenizing this technology and at the same time um, trying to make real world applications tangible by the introduction of classical and quantum compute in a harmonious fashion. It's also great to be a part of this session because we closely work with the academic community and universities and institutions. And I consider my privilege to be a part of this forum and with close to around 300 faculty members. Great to meet you all. So with that, I'm beginning my session. I would once again like to confirm if my screen is visible.
Yes, yes.
Okay.
Screen is visible, voice is clear. Please continue.
Right. So this is how I structured this session today. Quick purview into what is quantum computing. Majority of you may already be aware about this topic, so we'll keep it brief. A very quick introduction about QPI AI as well, the organization that I'm representing in here. And then I'll move to the industry viewpoint, what kind of applications we are developing today, how we see the technology grow into the long term. And finally, what are some of the challenges into the domain of quantum technology and how we are tackling those challenges and building opportunities for ourselves and for the entire ecosystem. So to begin, about what is a quantum computer or what is quantum computing is a broad domain. So quantum is a next generation computing technology. It uses fundamental principles of quantum mechanics to encode data and to process that data, process that information. And at the heart of it lies the qubit, which is similar to a bit, but it is probabilistic and it follows strict principles of quantum mechanics, because of which it can exhibit properties like superposition and entanglement. It's my assumption that you're already familiar with superposition, entanglement, and a qubit. My only point here is to emphasize the fact that these superposition and entanglement are resources that we use to design quantum algorithms, and these resources are quite useful when solving certain problems which are beyond the reach of classical computers and supercomputers for that matter. So the two powers of quantum computers or the qubits themselves come from the first aspect comes from the property of quantum superposition, which introduces an intrinsic parallelism in large vector spaces. And now, considering the kind of problem we are trying to solve, if it's an optimization task, intuitively you can understand that the quantum computer can try out multiple solutions at the same time. If it's a machine learning task, you can consider that you can encode exponentially larger feature vectors into the combination of qubits, right? So this kind of intrinsic parallelism is what makes quantum computers really attractive and useful for solving certain kinds of problems. Uh, Algorithms like the Shor algorithm or the Grover algorithm typically exploit this property of superposition to do computations much faster and in a parallel way. The second property is the property of entanglement, where multiple qubits behave in a special way which cannot be explained classically. And the core idea is that because of entanglement, the qubits can model complex correlations. And these complex correlations are important in various utility tasks or real applications. Consider financial risk modeling or consider the transfer of information across communication channels, or consider complex correlations that are represented as bonds in molecules and molecular systems. Right? So these are the two properties which are really useful, and we exploit these properties as resources to perform effective computation. And if we compare the bit versus a qubit, the differences are coming in because of the superposition state instead of a discrete state, the state being in a combination of basis states and being probabilistic while following the quantum mechanical logic. So that is the difference between a bit and a qubit, the fundamental or the unit block of information. At the same time, there are certain differences at the scale of the computing system itself, right? So, classical computer, which, for example, the laptop that I'm using, these are suited for traditional processing like document processing, small scale numerical computations, logical computations, etc. And these are really robust and noise resilient devices, right? You can rely on these computations because the error rates are really low, and they're easier to manufacture and scale because of the semiconductor based fabrication technologies. On the other hand, the quantum computers are suited for special types of problems that are typically currently solved using high performance computing. They may be associated with large scale combinatorial optimization or the simulation of quantum systems, or this could be machine learning in really large feature spaces. One of the aspects about current generation quantum computers is that they are noisy, and one of the endeavors for the entire quantum community is to build quantum computers that are error corrected and fault tolerant. And that is also one of the specific goals that we are following at QPI AI, and I'll talk about it in a bit more detail later on. And because of the fact that these are specialized chips and specialized devices, with various kinds of modalities, QPI works on superconducting qubits, but then there are other forms of qubits as well, like ion traps or photonic qubits, etc. So the engineering around these qubits are really it requires a great degree of challenging technological development. And why I'm emphasizing on this is because to our academic community and to our faculties, these are presented as opportunities because there are various research and development directions to build better qubits and build better quantum computers. And I'm sure that the community can contribute back and can also participate into this technology build-up. A very quick introduction to QPI AI, the organization that I'm a part of. Started in November 2019. We recently completed 6 years. I've been working here since 2020. And at present, we have three centers, one in Bangalore in India and two others outside of India. We're a technology rich company building full stack quantum computing. So we are building the quantum processors and also building the firmware and the application layer on the top of the quantum processor. We are privileged and fortunate to be a part of the National Quantum Mission. A lot of support from the Government of India and the Department of Science and Technology to scale up our technology processes and build next generation devices. And we have also been supported by various other schemes and actively covered across the tech media and several awards to our accolades. What you see on the picture is a 25 qubit quantum computer. This is based in Bangalore, in Karnataka. And this is the computer that is currently operational, the largest one in the country at this time. And it also has a high performance computing integration in the sense that what we have here is a module data center, which includes CPUs, GPUs, and QPUs with a unified software stack. And the software stack itself is mapped to various end applications like chemistry, material sciences, operations research, stochastic modeling, cybersecurity, etc. So that is what I mean by a full stack, right? So going from the processor to the all the way across the instrumentation to the end application. And this is a 25 qubit machine. And recently we have also announced a 64 qubit machine at TestTech 2025. So a 64 qubit chip is what we have announced, and it will be available next year for deployments and for remote accesses. This event was graced by the Honorable Prime Minister of India and also by the Honorable Minister of Science and Technology. And our 8 qubit chip was presented to the PM along with the announcement of the 64 qubit. So we are not stopping at 64 qubits, but scaling up to 128 over 2000 qubits in the next 2 to 3 years. And parallelly, we also have a roadmap for logical qubits and fault tolerant quantum computation to have 100 logical qubits by 2030. Now, to specifically talk about the industry viewpoint and also from our experience at QPI AI, what our experience is and the approach that we are taking. We are focusing on quantum error correction and building fault tolerant quantum computers over the next 3 to 5 years. And at the same time, we are focusing on integrating high performance computing and quantum computing to onboard majority of the HPC oriented tasks today and make those computational pipelines quantum ready. And there are several examples across domains, and I'll also highlight a few of them. So before I get into that, one of the questions that we are often asked is why do we need a quantum computing system, right? Why do we build a quantum computing systems? Now, For a reason, one is that simulation of quantum systems on classical computers is really hard. It's infeasible, and majority of the material sciences, the chemical industry, the drug industry depends on this kind of simulations. And statistics says that close to 96% of all goods that are produced in the world, they directly or indirectly have a material or a chemical simulation involved. So with the practical utility of simulation being so important, and with the fact that it's hard to model these kind of systems on classical computers, it's a natural need for people to build new kinds of devices that can support this. Along with that, there is a saturation in the traditional semiconductor capacity, because the scale of the chips, or the scale of the components on the chips, the transistors themselves, they are reaching a quantum scale, and the quantum effects, they disturb the reliable processing of digital signals in the form of overlap of states of 0 and 1. And there are considerations around energy, being energy is a consideration. So we are looking at other alternatives that can work at a quantum scale and are more energy efficient. And the third point is fundamental complexities around certain aspects of classical computing. So some problems are infeasible on classical computers, no matter what resources we throw at them. So they are bound by the computational complexity. So because of these kinds of reasons, we aim to build quantum computers and also integrate them with classical computers to make a heterogeneous compute that can solve real world problems. On the left, what you see are some experiments and results that were shared by Google across 2019 and 2024, which clearly demonstrated the need of, or I would say, the advantage of quantum computers over classical supercomputers in terms of their power, the speed of execution of certain experiments, and their energy efficiencies, and the time that it takes to solve those problems. Now, our view, or the view of the industry at large, is to bridge high performance computing and quantum computing, and that is being targeted towards certain specific kind of applications in combinatorial systems and complex dynamical systems, or into learning systems with high dimensional data or over parameterized models. That's where quantum computers will be really useful. And definitely some of the domains that have seen uh, significant adoption and exploration are around drug discovery, simulation of material systems, modeling proteins and their interactions with drugs, with quantum methods, and also the domain of operations research, which deals with mathematical programming techniques to solve real world problems. So that is the idea of the industry as of today, because as the complexity of modeling is increasing across use cases, like, so you're going from fundamental automation to analysis of data, you're going from data analysis into building learning systems, and from building learning systems you're moved into the era of intelligence. So as we have seen the transition from base automation to intelligence and more generative forms of intelligence, there is a big increase in dimensionality of the data and the complexity of the models. And that's where we see that for very specific areas like the scientific computing areas, quantum will give benefit, and it will give benefit in terms of speed, in terms of energy efficiency, and also make it possible to solve certain problems that were not possible earlier. So that's what our approach is, to focus on quantum and HPC integration today, run quantum inspired algorithms and hybrid quantum classical algorithms, and keep on scaling up for fault tolerant quantum compute in the future. Now, how the community here can participate is to, first of all, to explore this domain and pick up use cases and pick up research and problem statements that are important for the holistic development of their respective domains, like maybe biosciences, pharmaceuticals, agriculture, into material modeling or mechanical systems. Right? So there are endless problem statements that do exist, and right now is the right time to explore and get started into these kinds of research. So applications being across chemistry, biology, optimization, cryptography, and machine learning. So, what I'm putting here on the bottom section of the slide is to demonstrate that for very small systems, even with the system with the 10 electron and 40 orbitals, the number of configuration that the system could take is enormous. It's an astronomical number if we consider a chain of amino acids chain with 20 residues. The number of conformations or the number of combinations in spatial orientation it can make is an astronomical number. So you have small data to represent, but the representation space or the computation space is really large. And that's where quantum computers would excel, because they can do parallel computing and they can apply the effects of superposition and entanglement and interference to find out the right answers faster and with more efficiency in algorithmic complexity. So, based on this particular assumption that we have parallel computing and we have more efficient computing, quantum computers are being explored across the industry into domains such as security, domains such as chemistry, which is chemicals and materials, also into domains such as financial services, into complex systems like weather modeling, climate modeling, across agricultural domain into discovering crop yield optimization techniques, or genomics of the plants themselves to create better breed of crops, so on and so forth. So with that, I'm starting around the first example, which is uh, cryptography, how quantum computers can break RSA encryption, and the scale of the computation that happens here is the equivalent of comparing 10 seconds versus 300 trillion years. And this singular use case affects everything in the world. It affects countries, it affects organizations, it affects companies, institutions, universities, everyone. So the entire digital fabric is at vulnerability. And with some aggressive estimates, people believe that fault tolerant quantum computing will be available in the next 3 to 5 years. With some more conservative estimates, people consider it to be across 15 to 20 years. Whichever is the case, what is a fact is that the digital security is at risk even today and not only in the future, because the data can still be harvested and it can still be stolen and can be decrypted later on. And because of that, people are trying to shift to post quantum cryptography. So, one of the major industry viewpoint is to transition from quantum vulnerable security regime to quantum secure security regime, and we are actively working in that domain as well, working several healthcare institutions and financial institutions, both public and private, supporting them in how they can transition to post quantum cryptography. So, one of the takeaways here for the community is that it's one of the core problem areas for research and development. Please do consider working in this domain, and we are also actively working, so there are avenues for collaboration. Specifically for the community, you could think about building new kinds of security protocols or new kinds of code that can be resilient to future quantum attacks, so on and so forth. Second area of opportunity is across the domain of complex systems and the domain of combinatorial optimization, and typically into the domain where really large optimization problems are required to be solved. So consider thousands or millions of variables and thousands or millions of constraints. This particular problem can come across in any domain, any industrial domain. So, be it logistics, be it transportation, be it industrial processes engineering, manufacturing, Industry 4.0, IoT, construction, whatever you can think of, maybe railways, aviation, drug sciences, chemical engineering, material simulation, financial services, any domain that you can think of, mathematical optimization is present everywhere. And for certain use cases, the complexity cannot be tackled with current generation optimization techniques. And that's where quantum inspired optimization comes in. In our experience, we have solved use cases around design engineering, around telecommunication network optimization, around drug search, so on and so forth. So this is an active area of research, and to the faculties in here, uh, irrespective of whichever domain you're working in, you can start building quantum inspired optimization solutions for that domain by finding problems that fall within this kind of a structure of having multivariate, multi-objective optimization needs, having a large number of variables and constraints, and typically they can represent large scale graphs or networks. So that's a second opportunity. First was around security, second is around optimization. And with this kind of approach, the industries that can benefit from the quantum domain is all of these industries and even beyond this, right? So you can pick up use cases across these industries, and then you can build quantum models. There is a scope of collaboration with QPA AI because we do provide various kinds of modeling uh, platforms. So optimization solvers and quantum machine learning and quantum AI libraries. Along with that, we also provide high performance computing accelerated simulators where you can run these simulations. And we also do provide quantum computing runtime where you can access the 25 qubit machine and you can remotely run those calculations on the quantum computer. One of the points I want to highlight is for several of the critical sectors like defense or medicine or finance. Now, these are the sectors that are really critical to the security of the country. And one of the requirements in traditional computing, so non quantum computing, is that there needs to be data residency in India and there needs to be compute sovereignty. So even from that lens, if you are interested in working on building some quantum solutions, uh, it would be an advantage to have those solutions built on indigenous technologies, so that the solutions can in future be commercialized or can be taken up by the various authorities or the governments into more into translation into a product or a technology that can be commercialized. Now, with that, you know, application centricity across various industries, we translate that application centricity into usable software across logistics, pharma, and materials. And some of the examples I want to share from the industry viewpoint is from our experience of how we have developed. Is we are integrating the current generation AI and current generation HPC and bringing in quantum exactly where it is needed. Right. So I mentioned earlier that quantum is needed to model complex correlations. So we are treating only this part of the entire problem statement with quantum compute, and rest of the segments are being treated with classical compute. So this is a problem of modeling the interaction of drugs with proteins, and this particular technique can be used to determine drug efficacy. It can also be used to determine the protein reaction networks and pathways of how these proteins are responding to the drugs and how further disease mapping can be done. It's a very important problem in the area of both healthcare and also in the area of drug discovery. And what we have established here working with one of the large drug companies is that quantum computational techniques are much more resource efficient and can enhance the accuracy of calculation of these complex systems. can match the classical accuracies even today. And as the number of qubits increase, the advantage of computation is exponential, and much better computations can be done in terms of accuracy and speed. Second example is of quantum inspired algorithms. So these are classical algorithms built using quantum intuition, but can be executed on current generation processor. And here we have seen a significant improvement in terms of um, accelerating the overall process of car design. Now, for the faculties in here, if you are working in the domain of construction or sustainable architecture, into the domain of automotive or aerospace design, this is something to be. I would recommend that you look into this domain, because quantum inspired optimization has seen several successes in optimizing these kinds of design processes, and making this entire process much more sustainable, as well as accelerated in terms of time to computation. While on the other hand, if we have faculties who are working in the domain of uh, drug modeling, chemical simulation, or material simulation, this is one of the core areas of application of quantum, and they should definitely look into this domain as one of the priority areas. Third example is into the domain of transportation and applied across the transportation sector. In fact, the work that I'm sharing right now was one of our earliest works back in 2022. It was also featured in the Harvard Business Review as one of the first practical demonstrations of quantum computing, which made any real world impact. So, how transportation networks can be made more efficient, how the operations can be done in lower cost and at better speeds. And lastly, one of the other use cases in the domain of energy and carbon capture. So, how carbon capture processes can be made more efficient, how large scale chemical plants or large scale industries that generate carbon, how they can be aggregated into a single network, and carbon can be captured and then transported to various locations where it can either be stored or it can be utilized to create new forms. So, one of the points that I want to highlight right now, as I have discussed various applications, is that several of these applications have a huge societal impact in terms of sustainability, in terms of better agriculture, in terms of how it can enhance the quality of life of a large population like India. And there are various opportunities in terms of funded projects, in terms of grants from various departments like DBT, DST, MIT, so on and so forth, and also certain other private institutions that support this kind of next generation research. I invite you to you know, explore the domain, so that for your own areas of expertise and for your areas of application, you can discover and develop quantum solutions. And that process of development can be collaborative. We are happy to collaborate. We are happy to extend our runtime to you with support from various agencies. And there are various calls and grants that are already running to support this kind of application development. Now, the last segment that I want to cover is around the challenges of, as an industry, what challenges do we see? And being in industry and developing the technology, what we have seen is many of these challenges are not fundamental challenges, but these are more of an engineering challenge. And because of them being engineering challenges, our industry as a whole, or I would say QPIA in particular, we treat them as opportunities, because the technology is evolving so fast, and the technology is evolving into new directions. Because of that, there are several opportunities where these challenges can be solved, and better computers can be built and better applications can be developed using quantum. So the first and foremost challenge that we see right now is the noise in quantum computers. And this is essentially because quantum computers are fragile. They work at a level of a quantum system itself. And there are always classical disturbances that impact the functioning of a quantum bit. How we are tackling it or how we are treating is by building better qubits, by having new kinds of materials to build the qubits, by having error correction codes that can be more efficient in terms of the qubit resource, so on and so forth. So to explain this diagram, what you see is on the right, the number of qubits are increasing, and on the left, we see that the limiting error rate is, uh, actually also increasing. So what happens is, or you can inverse this and think about, this is a regime with low error and this is a regime with high errors. So based on that noise in the system and error in the system, you cannot really extract quantum advantage at very large scale number of qubits. So how NISQ applications are being used? They are being used to develop algorithms, secure that intellectual property, and have a demonstration or have a proof of execution where certain problems being applied to the quantum model are functioning as expected, and there is a potential to scale. This is the most important research direction as of today, proving that these algorithms work as expected and they can scale up, deriving advantage using hybrid quantum and classical systems, which can be utility scale and continue to scale up for this domain of error correction or a fault tolerant quantum compute, where the advantage can be amplified. Well, some of the constraints today are noise thresholds, as I'm talking, also the number of qubits, how the qubits are connected, because that directly impacts the entanglement between the qubits, the depth of the circuits that can be executed, and also what gates are supported for a particular kind of hardware. So, the approach for the industry today is to attack these challenges and work with quantum inspired and hybrid quantum classical computing in the near term, and continue to scale the technology towards building a more resilient, fault tolerant quantum computers, such that this entire architecture of high performance computing, next generation AI, software, and quantum computers, it converges towards quantum and supercomputing in a combined fashion, and it can solve some really important problems. Some of the technology frontiers today of how these the challenges are being solved is, first of all, these are the areas of priorities, like building quantum error correction, building better integration of HPC and quantum, having new kinds of qubit materials that can reduce the dependence on low temperature, or inherently increasing the performance of the qubit. Hot qubits, in the sense that the qubits can operate at relatively higher temperatures, and that is also an active area of research. One of the other areas is into building systems that connect quantum computers and enable distributed quantum computing. This is also one of the domains. And into that line, recently, we had in November itself, we had announced the Quantum Supremacy Center, which is essentially QPA AI's concept of building distributed quantum compute by connecting a fleet of quantum computers and scaling up the high performance compute around the quantum compute to build very large scale quantum data centers, which can then in future be connected to quantum networks and enable the cloud version of quantum computing. So these are some of the directions in which the research is advanced today. Definitely, the faculty groups here and the academic community should look into this domain. Now, apart from the engineering challenges, even bigger challenge today is to have people that are skilled enough that can contribute into either the development of quantum technology or the applications of quantum technology. So talent is one of the key bottlenecks, as we know, and the academic community is the best place to get started uh, uh, in terms of building that talent, right? So universities adopting quantum computing as a technology into their academic programs, building labs that can build quantum skilled engineers, both at the level of hardware and software, and starting with the research projects that can then be taken up towards large scale implementation, technology or product development or commercialization. So talent is one of the key bottlenecks, and we have seen that this is not just a problem in the country, but this is a global problem. There is a ratio of around 1 is to 20 for the number of opportunities that are available versus the number of people that are skilled enough to do that kind of perform that kind of job. These are estimates by McKinsey, by the way. So we definitely know that there is a demand for quantum talent, but at the same time, there is not enough quantum talent available, especially for companies like us, where talent is a key bottleneck in terms of scaling. So how we are addressing that challenge is we are partnering with institutions, and we are building models where the academic community can benefit from availability of quantum resources to them, right? So one of the ways in which we engage with the universities is to deploy quantum computing systems on premise within the university. And I would like to highlight one aspect here is that traditionally we have seen a fast adoption of software based skilling. We are the leaders in software and IT across the world, but the same adoption was not seen with semiconductors and also was not seen as much with modern AI. And the reason is because the engineers or the scientific community is not exposed to systems in terms of the real physical systems, but it's mostly limited to a software defined interface and mostly limited to coding practices. So, with that being one of the challenges, as we have seen in the community, and that's what we feedback we got from the universities that we work with, we started this offering of an 8 qubit quantum computer, which can be deployed within the universities and can be opened up across various kinds of streams. Like, for example, fundamental and basic sciences for studying the device physics or the qubit physics itself, various AI, machine learning, computer science, information technology, cloud engineering. These domains can definitely benefit from various aspects of quantum software, quantum programming, quantum algorithm development. And this direction, particularly, is quite suitable for research areas in the domain of quantum as well, and especially because of the support that is being extended via the NQM. Then there are opportunities for engineering streams like mechanical, where they can learn about cryogenics of quantum computers, or chemical engineering domain, more around the chemical processes into the overall device engineering, and especially instrumentation and control, because the quantum computer itself is a complex system, and it's a challenge to control and make the systems functional. So a lot of these aspects of control engineering fall into place into how a quantum computer operates. So with the availability of this kind of a system, the students and the faculties can not only learn about how these systems work, they can also get deeper into the research areas of how maybe the control of a quantum system can be optimized, how the control systems can be built with better digital electronics, or how qubit design or the chip design can be enhanced to build better computing devices. So that is sort of a lab linked and interdisciplinary learning across the engineering streams. And along with that, not just having the infrastructure for training but also for research, as because of having a physical system you can work towards new ip creation, filing patents across the domain, and ultimately collaborating with industries to provide them solutions onto quantum computing in the form of sponsored projects or in the form of various kinds of industry based support to explore a new tech or a new scientific domain. And finally, it also is ultimately important to attract projects of national importance from various competent agencies that are actively pursuing this domain and working towards enabling the adoption of quantum technology across multiple verticals, both in the industry and in the academia. So these are several collaborative ways forward for us, and I directly invite the community and the broad forum here to engage with us and with companies like us across the domain. Specifically from QPI side, we are actively involved into skilling faculties with exposure to quantum systems and quantum hardware, supporting institutions into initiating and operationalizing degree programs like bachelor's or master's in quantum. Also, partnering with institutions towards several projects that are released under the National Quantum Mission, and to also facilitate the interdisciplinary research areas like several examples I had given around chemistry or design engineering or transportation, etc. And also to build a foundation where not only the quantum mission but also other synergistic missions like the National Semiconductor Mission, the National Supercomputing Mission, or the mission on cyber-physical systems, all of that can converge, and with our joint efforts we can create something meaningful, both for the institution and also for the country at large, and build a strong pillar in terms of the global quantum landscape and compete with the world. So with that I'll stop, and this is in case if anyone is interested to get in touch, please do. I welcome your connects and welcome further collaborative opportunities. So with that, I'll stop and would be open to any questions. Otherwise, I would say that Dr. Pilli can coordinate.
Thank you so much, sir. I request participants, if you have any question or doubt, or if you want any discussion on this topic, please put your topic in the chat box. So, sir, there are few one or two questions there in the chat box.
Okay, which one would you want me to take?
Sir, accordingly, you may just refer them if you think it is related to the session that you have taken. You may just address them.
Okay, so one of the questions is from Rahul Rantala. So hi Rahul. So you can reach out to me. My email is on the screen, and that I can introduce you to my teams who are particularly involved into the training programs, and they can take it forward with you. So second question is with from Dr. Kupuswamy. What kind of courses to be taught for BTech students? So there are certain foundational courses like introduction to quantum mechanics, introduction to mathematical foundations of of quantum computing or quantum technologies. Then there are other core quantum courses like quantum introduction to quantum information, introduction to quantum algorithms and computing. So this forms the second year of studies, and then there are specializations like quantum optimization, quantum device engineering, quantum security, quantum chemistry, so on and so forth. In fact, AICT had released a recommendation last year about programs in quantum technology, and also recently there has been an announcement of the MTech programs in quantum technology and quantum computing from AICT. The QT-03 and QT-04 title, as you see from this session, is also aligned with the syllabus structure of the AICT recommendations. So, if you are interested into running these programs, please feel free to reach out to us. We have academic training systems and academic training platforms and programs that are strongly aligned with these AICT recommendations, and also provide hands-on access in the form of libraries, in the form of access to our compute and to our simulators as well. Uh, One of the highlights here is that to the group of universities or universities that can actually house a quantum device within the university, there are opportunities for courses in electronics of quantum control. There are opportunities around cryogenics of quantum computing, also into the chip design and the qubit engineering aspects. So even that is a part of our comprehensive, platform. So the next question is around use case of in classical statistical physics like spin glass. Absolutely yes. So majority of these spin glass systems, they actually form the basis of quantum optimization. I can give two examples. So one of the concepts around Ising systems and the interaction of spins form the basis of quantum inspired optimization techniques that can be solved using some of the graph relaxation techniques or tensor network based methods. Other example of classical statistical physics reoriented towards quantum computing is into developing quantum neural networks, and much like Hopfield network in classical machine learning, there are directions where the spin glass based neural networks can be used for building parameterized quantum circuits. Uh, so there are also a few other questions. I'd be happy to respond to them. You can write to me, and I'd be happy to respond to them specific to your query.
Yes, sir. I think time is also, we have short of time, but maybe one question, maybe you can explain to the participants about the full stack development when we look at a quantum hardware, the quantum software. So any challenges, because I am sure QPI has a stack ready. So can you share a little bit about what are the challenges in also building that whole thing? Yeah.
Yeah, so one of the core challenges are around controlling the environment of a qubit. And as you may have seen in my picture, that we have an elaborate system to bring down the qubits to cryogenic temperatures of close to 7 to 10 millikelvin. Right? So that cryogenic system development is a challenge uh, because qubits are inherently fragile, and to build the full stack, it is really important to have high quality qubits. And though it's an engineering challenge, I can also say that solid state qubits like superconducting qubits are highly stable. because of operating at a cryogenic temperature. So that is one challenge which is largely which determines how well a quantum computer works. Other challenge is into the development of classical software of a quantum computer, right? So how can we build compilers that are really optimal and can preserve the quantum advantage? And it's like so the question is, are we not losing quantum advantage because of classical overheads, right? So that is one of the core challenges, and that's also how we are solving is by building application optimal and device specific compilers. So that is another challenge, and the third challenge is to tune qubit, right? It's very difficult to tune qubits to certain frequencies where they can perform, and how and it's manually it's not just possible, right? So there are automations for that. How we are solving them is by automating the process of qubit tuning and qubit calibration, and also using a sort of intelligence and AI by learning from various kinds of uh, qubit characterization and calibration data and making that entire process automated. So these are some of the challenges that we have faced as a full stack company, and these are the ways how we have tried to solve them. I would say that not all of the issues are solved, because as the technology keeps on scaling, as we go from 25 to 64 and beyond that, we will see new challenges, some that we may not have seen previously. And that's where we need people to help us out in terms of talent, skilled engineers. And that's why we are so focused on building that ecosystem here in the country, and working towards these scalable systems.
Yeah, maybe the last question, maybe because we have a few seconds left. You are integrating AI with quantum. So is it going to be a difficult challenge to build algorithms to integrate AI on quantum? Maybe quickly you can answer and then we can conclude.
It is in a way, because many of these domain specific AI is not really trivial to build. And the way quantum algorithms are designed, they are fundamentally different from classical algorithms, be it AI algorithm or a search algorithm, etc. So the challenge here is more around having the necessary skill to merge AI and quantum. How that can be done is non-trivial, and how we are solving this is because, first of all, our philosophy is to integrate AI and quantum. That is our core expertise. Along with that, we are also applying AI to discover quantum algorithms, right? So learning from the quantum uh, algorithmic structures, and then applying AI to discover novel algorithms is something that is of core importance to us. And in that way, there is sort of the next generation quantum AI coming into picture, that we see can evolve into something really big.
Yeah. Thank you so much for your valuable time and sparing almost a full 1 hour with us. And participants, hope you have really looked at what are all the things that are going on and what are the challenges. And of course, there is a long way to go. And as he rightly pointed out, there is a skill deficiency, and you are the right people. About 400 to 500 of you are here today listening to this talk. But here we have a good example of the challenges that are being addressed. It is not that theoretical. Please don't think quantum is still theoretical. Here are some live case studies which are happening, and business is being generated. And of course, people are also bringing this. So thank you so much, Mr. Lakshya Priyadarshi, for sparing your valuable time. I think it will run into lots of, if you look at a financial calculation, it will be too much. But thank you so much for being with us. And yeah, I will pick up a few questions which they have listed. In case they're very key, I will pass it to them, and then you can answer quickly. Yeah. Thank you so much for being with us. And from the bottom of our heart, we thank you so much for being here. I was looking forward for this session, and thank you so much. And of course, we have the next speaker also ready with us. So thank you, Mr. Lakshya. And this time we'll welcome Ms. Janani also from IBM, Quantum Bengaluru. So maybe you are aware of each other, so you can say hello. And
Hello,
Yeah.
hi Janani.
Hi, Laksha. How are you?
I'm good. How are you?
I'm good.
Great,
yeah,
great to meet again.
Likewise.
yeah. Thank you so much. So
Thank you,
participants,
thank
we
you
will.
all. Great meeting you, and look forward to being in touch.
Sure, sir. We'll interact with you. Yeah, thank you so much. So participants, after this wonderful session on QPI-AI, we will move to the next session by Ms. Janani. A lot of things have been discussed with us in the last few lectures that ma'am has taken. And we were just looking at some things while we were discussing some things which we could add up more and more on a hands-on thought process. So here we have, without wasting much time, I would want Janani madam to take it forward. Break करेंगे क्या session? So Janani madam, over to you. Thank you so much for joining again. And
Thank you, sir.
she is in the midst of a development session on QuizKit. So, but she said, no, I have already agreed. So let me take this session. So I will listen more from her later. But in this, we will have the hands-on demonstration. Over to you, ma'am. Thank you.
Thank you, sir. It's always a pleasure to be here, and I'm glad to be able to, have this session with the participants. So, the idea of this session last time, what happened is that we had, I tend to take questions in the middle of the session, and last time, 40 minutes plus went on with the question answer discussion, which I did enjoy. But since there's been a lot of request for hands on, this session I wanted to have so that we can see the implementation. And there are several things. Firstly, I would like to mention that if you go back to the slides that I have shared, there are snippets of code. So if you kind of work with that, you should be able to kind of do the hands-on yourself. But it's different when you have a walkthrough of, say, a very simple toy problem for, say, an algorithm like VQE. So from start to finish, or at least like to get started somewhere, what do we do? That is the aim of today's session. And what I have in mind is to first show, as I mentioned, a very simple toy problem. And for algorithms like VQE, and even outside of that, one of the crux or core ideas of quantum computing involve expectation value estimation, and that forms the basis of several algorithms including VQE. So how do we do that? And how do we deal with observables? So even before, if you remember the Qiskit patterns framework which I showed, there are 4 steps in that, right? The first step is to map your problem to quantum circuits and quantum observables, and then for the next step it is to optimize your circuit for execution on hardware. And then there's step 3 and step 4 where you actually do the execution, and then in the fourth step you do the post processing. So all that is there, but before that you need to understand, like in the first steps itself, how do we go from, what's the like workflow, right? And you can look at applications, but it's not going to be it's not going to it may not drive in so much clarity, because there's going to be a lot of problem dependent parameters also when you're looking at a use case application. So if we have time, I will go through at least the workflow of what happens in a use case application. But before that, I want to show a simple quantum algorithm walkthrough workflow, which we would see on, say, by using a quantum simulator, just to be able to get the results and know that our VQE is working, right? So say I'm developing a new algorithm and I have my quantum circuits, I have my observables, I have a way to, do some expectation value estimation, and I know where I want to put it in, put it in the workflow through an estimator or a sampler. I mean, if you're using a sampler, you can still do expectation value estimation, but I'll come to that later. But yeah, so what is the workflow? Say I'm developing an algorithm and I want to test it. And once I have it like in a good shape, I can test it on a simulator or a fake backend. And once that is also done, then you can look at how you want to apply it for a specific use case. Say, I can use VQE for so many things. I can use VQE for, calculating ground state energies of, like looking at the ground, basically solving quantum chemistry problems. I can do that. I can solve the traveling salesman problem. I can do combinatorial optimization. I can do several things. But before that, how does a VQE work? So let us get into the session. Just give me a second. I will share my screen and we can get started. So this, I am actually starting with sort of an old version of the notebook. And the reason I want to do this is so that I can show what kind of errors can pop up. Like if you're using some old version of notebooks, and how do you, how can what kind of change should I make to get my, notebook to work? So yeah. You will see some deliberately introduced errors, and we will see how to rectify them as we go. Okay.
Ma'am, you have not shared yet.
No, I haven't shared yet. I'm
Yeah,
just,
sure.
now it should be visible.
Yes, ma'am. Finding
Okay.
minimum, maximum. Yeah.
Yeah. So, okay, for this notebook, just mainly using Qiskit alone. No Qiskit runtime because I'm not running anything on hardware. And I mean, like there is some basic provider and simulator stuff you can use via Qiskit itself, but I think I'm using Qiskit Air in the end. But let's see. Let's just get started and we can go. So, what is variational quantum eigensolver? So very simply put, VQE is an algorithm which helps you find the eigenvalues of of a given Hamiltonian. So if you have what is a Hamiltonian? So a Hamiltonian is an operator. Specifically, it is an observable which corresponds to energy. So if we know that in quantum computing, how do you know the state of a system, of a quantum system? You have to perform a measurement, right? So unless you perform a measurement, you know nothing about the state of the quantum system. So if I want to measure the energy of a quantum system, which I cannot know unless I do some measurement, how do I figure that out? So like in quantum mechanics, observables are quantities which or special operators, you can say, which correspond to some real, true, measurable physical quantity. So if you take the Hamiltonian, for example, it helps you calculate the average. It returns the energy of a system. So if I want to calculate the average energy of the system, I will do that by looking at the expectation value of this observable, which is the Hamiltonian. So with that in mind, that is the Hamiltonian. And if I want to find the eigenvalues corresponding to that Hamiltonian, I can do that using VQE. So for many problems in math, physics, and chemistry, you need to estimate the minimum or maximum eigenvalues of a system. And classically, for very large systems, it is difficult to do this in a straightforward manner, which is why we use some kind of variational methods to kind of derive them. So let us get, so say for example, you cannot start off without like being anywhere in a variational method. You need a good first guess, and that guess is, say, given in the form of psi of theta. So we will see what psi of theta is in more detail as we go. But so once you have this good guess, you can calculate the expectation of this operator L, say, for which you want to find the minimum eigenvalues. For example, you can say that the expectation value E is nothing but like you have the expectation L equal to psi of theta, bra psi of theta, L ket psi of theta. And when you calculate this quantity, you are able to get an estimate of this particular, this will sort of serve as your cost function, okay? And this variational form ensures that lambda min will be less than or equal to this particular quantity. And so when E is equal to lambda min, you get the minimum value. But so that will be possible only when you get the perfect guess. So what is the thing you're guessing here? You're guessing theta. So psi of theta varies with theta, obviously, as it is a function of, as it is a function of theta, or you can say more specifically that it's parameterized in terms of theta. So as you guess theta, different thetas, you calculate different costs, and you try to pick the minimum one, or you drive it in such a way that the next so you use a classical so in VQE the classical optimizer use comes here. So you want to once you guess a specific value for this psi of theta and you calculate the cost, you would like to know what would be a better guess for theta, such that in the next iteration you're actually getting an even lower value. And when you have attained the perfect value, what happens is you've guessed the best possible theta. So when at the best or perfect guess of theta, you will get E equal to lambda min, which is what you wanted to find, or that is basically the eigenvalue that you wanted to find. So for implementation in a quantum computer, the operator is expressed as a sum of Pauli operators I, X, Y, Z. And we want to find the minimum value of the matrix, say, let's say, for example, A is equal to 2, 3, 3, 6. Now, a small interlude here. One thing to keep in mind is that now this is looking like very quantum mechanical and complicated, right? But say you're someone from a computer science background. You can mathematically interpret this. This is nothing but matrix multiplication going on. L is going to be a square matrix, and psi of theta, like this will be a row vector and this will be a column vector. So bra psi of theta is a row vector, and ket psi of theta is a column vector. So you have a row vector sandwiching say a square matrix, and you have a column vector. So what will be the end result that you get? So you will get a 1 cross 1 scalar at the end, which is why lambda min is sort of the value that you can figure out by doing this. So ultimately, while you know that we know that these are quantum mechanical quantities, to interpret or understand what's the underlying mathematics, you can think about this as matrix multiplication. Of course, there's quite a bit of nuance here, especially in terms of observables. So this is for a 1 qubit case. Okay, this is not even 2 qubits. This represents a 1 qubit case. But when we go to cases like 2 qubits, which is the minimum of what you can expect when you look at use cases, say for example here, where is it? Yeah, I think this is the minimal example I had. So if you look at here you will be using at least 2 qubits. No, we are using 5 qubits. So when you have 5 qubits, how do your observables look like? They definitely look different. They don't look the same. Okay, so this is just the single qubit case. Now let's go to those details later on. But if I want to find the eigenvalue, you can also now again think of this, reduce this further and think of this as a purely math problem. Forget any use case, forget observable. So if I have a matrix A, you know that you can find eigenvalues for like matrices also, right? You can do a decomposition and you can find an eigenvalue for this problem. So if I want to do that, and if I want to do that on a quantum computer, how could I possibly do it? You can frame this problem, toy problem, that way. So now A can be written as a sum of Pauli operators. Now we are into QT-03, 4, so I'm not going to go back to what are Pauli matrices. That's like really basic. So we know the identity is going to be 1, 0, 0, 1. X is, I believe, 0, 1, minus 1, 0, or no, it's 0, 1, 1, 0, and Z is 1, 0, 0, minus 1, right? So if you kind of, you can decompose this matrix in terms of Paulis. Most matrices, to be any matrix, you can, this is just a 2 cross 2 matrix, right? But any 2 to the power n cross 2 to the power n matrix also, you can decompose it as a sum of Pauli operators. Pauli operators, and it's not purely just I, X, Y, Z. It could be something like, for bigger cases, you can have Z, Z, X, X, YX, YZ, those kind of terms also you can have. So now I can write, now for this toy problem, I'm writing A as a sum of these Pauli operators as follows. So I have minus 2Z plus 4I plus 3X. Why do I want to do this? It's because I can, when I want to calculate the expectation A, I can express it as this, right? And when we have to estimate expectation values, doing that for poly operators is going to be relatively simpler. So I can write A as minus 2z plus 4 plus 3x. So this is a problem. Okay, yeah, let's just go down. So as mentioned here, this is a problem that can be solved using a single qubit system, as our matrix is of size 2 cross 2. So we will create our ansatz by applying the U gate to 0. So, okay. Now, when we talk about a good guess, this psi of theta, what does it mean? So let me try to give a good example here. Okay, so if I have say I'm doing some experiment, right? And and I have a bunch of data points, I'm just trying to I am looking at a randomly moving car on the road, and I want to plot its velocity as a function of time. This is not like your typical physics, Newtonian physics class, where you have perfectly moving cars, right? The velocity of the car could be any kind of function of time. We don't know what kind of acceleration is there, right? Your acceleration could also be dependent on time. So to and understand that, or I don't know anything about the velocity of that particular car, so what I do is I watch it moving on the road, and I record the distance it is moving or displacement that it has had over time, and I'm just kind of jotting I look at the distance traveled and I plot a bunch of points. Now when you plot these bunch of points, how do you actually figure out the function of what the velocity is as a function of time? You will try to do a fit, right? So to do this fit, you need to come up with a guess. So even for wave functions, how do we solve if we see a wave, we need to come up with a guess to solve like how that wave is moving, right? So what would we say? We say that the wave is of the form a e to the power minus kx plus b e to the power kx or something like that, right? We come up with some kind of arbitrary function, and then we try to figure out the coefficients. So it's not exactly that here, but what we're trying to do is similar. So we have our solution, like we have a problem. Our solution is there, but it kind of exists in the void. We don't have any structure to explore through possible candidates of solutions. So to kind of give that structure, we now by parameterizing we parameterize the solution space and give it structure to explore across. So by saying that the solution, by kind of coming up with a candidate solution which is in the form of psi of theta, under specific conditions, we know that the ideal theta will behave in this particular way. In this case, we say that when I take the expectation value of L with respect to the ideal psi of theta, I know that it will give me the minimum energy, right? So that is the condition. So the way you kind of parameterize this psi of theta, it can be in multiple ways. There's no single way. But what is important to keep in mind is that the better your choice of psi of theta, the better your solution is going to look like, because it increases the chances that you find the right solution in the kind of structure that is created by parameterizing your solution space. So okay, u of theta. So now if you go back to the very first block sphere lectures, we recall that any movement on, say, so if I take a particular state from the block, we take a state on the block sphere and take it to any other arbitrary state, I should be able to model that as a rotation on the block sphere. So ideally, if I want to take a state and move it all across the block sphere, what kind of rotation would work best? It's a U3 or a three-dimensional rotation. So a rotation which acts on the X, on the Y, and the Z axis will help me move all throughout the block sphere, especially for the single qubit case. So I will say that I'm going to create an ansatz or a general state. So the most important thing here is that by using the U gate and implementing it to 0, I can have, say that I will have some alpha rotation along X, some beta rotation along Y, and some gamma rotation along Z. I'm just saying this qualitatively. There's a bit more to it on what the general state looks like. There is a phase component. There's many things. So I don't want to make it sound complicated. So like I'm just describing it more qualitatively, right? So, but it's true that the U gate requires 3 parameters. So yeah, now I use the U gate and implement that on the ket 0 state. And now I have a candidate solution or I have a state which kind of represents all possible states on the block sphere, right? By picking specific values of the 3 angles or the 3 parameters, I will be able to go to any state. So that is the point of an ansatz. An ansatz should be able to sweep over as many possible candidate solutions as it can. So now in this case, say for example that I'm creating my ansatz by applying U gate to 0. So it requires 3 parameters. And here I'm now first just defining this matrix. Okay, A is 2, 3, 3, 6. So we just now what we are doing here is we are finding out the ideal solution. You can use a classical solver by invoking linalg and .ig, and it helps you find the eigenvalues using numpy itself. You can do that. So for comparing my solution, I'm calculating the eigenvalue using this numpy linear algebra module. So it's 0.3994 and the other is around 7.6. Now let's do the same thing using a quantum computer, or let's do the same thing on a quantum system, say, or quantum computational method. So yeah, I'm just saying that my U is a function of some params 0, params 1 and params 2. Where did I define params? Okay, this is just the circuit definition. So I'm starting and I'm implementing this U gate on the qubit 0. And this is just the variational circuit being defined. So if you see here, I'm just randomly picking my initial state. I can enter this multiple times and it will change every single time because this is my initial state in VQE. And to be honest, in VQE specifically, the initial state makes a huge difference. We'll get more on that later, but if I'm running a VQE on hardware, I will never not run it on a simulator first. I will always run my VQE on simulator first and then hardware. Why? Because normally if you just ad hoc run like a VQE on like real quantum computers, of course it can converge quickly and all that, but you may end up consuming a lot of usage, right? So it's much more efficient if you first run it on a simulator, get to a decent result, and at the end of the optimization loop, you will come across a theta which corresponds to some minimum lambda. So now when you run it on a quantum computer, what we do is we supply the result of what we see in a simulator and supply that to the quantum computer. And now not only will it take lesser iterations to converge, but you will have a much more optimized optimized and streamlined way to like for the optimization to happen in the quantum computer itself. So that way, and you will get even better results. So this method is called as bootstrapping, or like we also say it's to warm start a QAOA or a warm start a VQE. So that's just a side note, but do note that depending on the starting position, the optimization path can vary greatly. You can immediately converge if you pick a good one, or it may take quite a few iterations. You may even end up in some like you may get stuck in some local minima and it might not converge for many iterations also. That is also possible. So that's why it's really recommended. You don't want that happening on a quantum computer, right? So that's why it's always recommended you run it on a simulator first. But again, for simulator, there is a finite length to which you can run on a simulator. This is for a 1 qubit circuit, right? For 1 qubit, we are using a 2 cross 2 matrix. For an n 2 to the power n cross 2 to the power n sized matrix, this is not like 2n cross 2n or n cross n. I'm saying 2 to the power n cross 2 to the power n. So for say 10 qubits, I would be working with a 1024 cross 1024 sized matrix. And honestly, if you just run a simple simulation, whatever we're doing here, even with like a high performance Mac computer, the best you can go is up to like 13 to 15 qubits. So you can compute matrices of the size. To be honest, that itself is a bit higher. You can yeah, like if you're just running everything plain without using say a quantum SDK or optimizing your work routine, just at like 12 qubits you will start finding that your computer struggles. So that is another reason why we need quantum computers, right? So yeah, coming back to the workflow, now let us estimate this observable z. So we said that a is nothing but minus 2z plus 4 plus 3z 3x. So let us first estimate the expectation value of z. So the result of this measurement, so okay, now when I have a 1 qubit circuit, what are the possible measurements? I can either have 0 or I can have 1. There is nothing else, right? And these are both eigenvectors of Z, which is the observable, which if you remember the whole discussion about computational basis and Hadamard basis, you will recall that if you take the Pauli matrix of Z, Pauli operator Z, you know that the eigenvectors of Z are nothing but 1, 0 and 0, 1, which corresponds to ket 0 and ket 1, right? So when you act like Z on ket 0 or ket 1, the eigenvalues you're going to get are 1 and minus 1 respectively. So Z will be equal to the number of times we have 1 minus the number of times. Yeah, so this is just a thing. Let us just look at what this will look like. So for example, let us say if I have ket psi, which is represented by the state C1 ket 0 plus C2 ket 1, then ket psi Z ket psi bra psi Z ket psi is nothing but C1 squared minus C2 squared. This is what the expectation value will look like. Where here C1 square is nothing but the probability of 0 and C2 square is nothing but the probability of 1. If you look at the state, we know this is obviously true, right? Zero's probability amplitude is C1, so the probability of its probability will be mod C1 square, and for this it will be mod C2 square. So first let us do this with the simulator and let us see how to calculate the expectation value corresponding to Z. So here we are using Qiskit-air. So as I said, we need to use Qiskit-air here because like initially air was a part of Qiskit, but now it's a part of Qiskit-air. So I'm using the sampler from Qiskit-air. So there are several options of samplers that you can use, and matrix product state is honestly the best. It's one of the best. The simplest one, you have QASM simulator. So each one, you have state vector simulator, QASM simulator. These things do different jobs. Yeah, I would recommend you go and take a look at the documentation about how each one is different. But with some approximations, you can kind of keep scaling up the size of circuits that you run using the matrix product state simulator. So, and here I'm supplying 10,000 shots. So after initiating the sampler, now what we do here is I'm just creating a copy of the circuit and then applying a measure all, and then let me break here so that you can see the circuit. So if you see here, this is the circuit. It's just one gate with a barrier, a measurement, and yeah, that's the circuit. So now the result, I say sampler.run of the circuit, and I get the result, and then I get the counts, and I will print the counts. So if you see here, the counts, it is 0.1122, and so this is basically C1 square and this is C1 square and this is C2 square. So now I want to do count 0 minus count 1 because this will be my expectation value of Z, and I'm plotting the histogram. So let me actually separate these lines so that we can see. Oh, Z. You want to break it here, and so what is count 0 minus, let me print ZZ. So it's 0.756. And what does the histogram look like? This is what it looks like. Okay, so for this particular initial state, this is what I have gotten. Is it guaranteed that every single time I will get this result? No, it will change from run to run. And if you want to actually get the best sort of average, like this is another good practice, and it is actually absolutely necessary when you tackle real life problems, because sometimes you end up with a good hand, sometimes you end up with a bad, bad sort of choice of like initial point. But if you kind of choose 10 different initial points and you do this experiment, like here we are already using 10,000 shots, so you do each experiment a few number of times and then you do the average of the results, you are bound to get a very reliable quantity. So now for example, let's do that right now. Okay, here now we've gotten the estimate of ZZ to be 0.756. Or maybe I leave that as an exercise because it's already 4:30 and we have quite a bit to cover, so I'm not going to take too much. Let me leave that as an exercise. What should you do? It's very simple. So if you just run like initiate the circuit different times. So if I run it again, for example, it will create a U gate with different parameters, right? So do that, say 10 times. So first start with one circuit, come up to this point where you've calculated ZZ, and then now repeat this the second time, and then you do it, and then you'll get another value for ZZ. So let us see an example of me doing it one more time, and then I will leave it as an exercise. So it's 0.6. It's not too far off, but it's a little bit far off. So now it's going to vary a little bit. There is going to be a range over which it varies, right? So that's why when you take all these different quantities, say if you do this 10 different times, we want to add all of them and then divide by 10. So basically the average. So then the quantity that you get for this Z variable is going to be much more reliable than just doing the whole thing once. So yeah, that is part of the assignment. Now we're doing the same thing for X, right? So in a quantum computer measurements, so now for the process for X is going to look a little bit different from what we did for Z. Why is this the case? It's because of the basis. So Z is so in a quantum computer, like at least in IBM systems, your measurements are always performed in the Z computational basis. What does it mean? When you get the counts here, it's also always going to be in terms of 0 and 1, or these corresponds to ket 0 and ket 1 states, right? So it's never going to be like plus. If you want to calculate Z the simple way, the same way that you're like the same. So sorry, if you want to do this for X the same way that you want to do it for Z, then you need to be measuring it in the Hadamard basis, which will give you counts in terms of ket minus and ket plus. I mean, that's what it should, but measuring that state is going to be a bit more complex, right? So that is why in a quantum computer, it obviously makes sense to always make your measurements in the Z computational basis. But how do you estimate an X expectation value in such a case, right? So X can be estimated by expressing X in the form of Z. So how do you do that? You can decompose X as HZH. You can do this and see X is nothing but HZH. So if I want to calculate psi x psi, that is nothing but psi h z h psi, and this is in like further nothing but psi h z h psi, right? So this is equivalent to finding a z after operating an extra Hadamard gate on the ansatz. So when I make this circuit initially, if I just add an extra Hadamard gate here before the measurement, then it is equivalent to measuring the X or X estimating the expectation value of the X observable. So here now we copy the same circuit and we implement a Hadamard, and then we put a measure all, and then we do the same thing which we did for the previous case. So let me just, first let's run this. So if you see here, you have a extra Hadamard. Now I will print counts. So run this on the sampler and get the counts. Then what is the X expectation value? Print that. And then I can plot the histogram. This is what it looks like. So now if I want to calculate the overall expectation value of that operator, it is nothing but minus 2 ZZ plus 4 plus 3XX, and you get the eigenvalue. So it's a bit off here, but let us just work with it and see where we go. So we started off with a random set of parameters and reached a value XX using 100 sorts. We actually used 10,000, I think, for calculating the expectation, but this is not this is not close to the expected lowest eigenvalue of 0.39. So we have to further optimize the parameters using an optimizer, which will form the classical part of the system. Now this is where we go into the VQE workflow. This is simply about expectation value estimation. So I'm just going to take a second to go to this implementation of QAOA on hardware. Why is because if you look at, so QAOA has a more complicated cost function. Actually, a simple VQE would have a more simplistic, this thing, like you'll have a simpler cost function. But what you don't see happening, like when you use Qiskit, is when you create the observable, you can simply mention it in terms of, you first simply create a matrix which represents your observable, and you can decompose it in terms of sparse poly operators. So if you see here, we have broken it down in terms of poly operators, right? So all this, like, it will automatically do for you a quantum SDK like Qiskit. So the reason why you would be more comfortable doing coding using, say, a quantum SDK rather than just say your plain Python, Rust, or Julia or whatever, is because it does all this for you automatically, or it provides you some kind of functionality to ease you into the process. Okay, so on that note, so like when you have observable, so this is just a single qubit circuit, right? So for, say, a utility scale QAOA, you will be working up to 120 qubits. So for 120 qubits, how many terms of Z and X do you think there will be? Each term will have 120 terms. So that is another nuance. Maybe I will go into that. We will see that as we keep going. But it does several things for you. Now we will see further as we keep going. So the next step would be to look at the actual VQE workflow. What happens in VQE? You have an ansatz, it will prepare a cost function. It will prepare an initial state. You calculate the expectation value of that state. Then you take the cost function. So that forms your cost function, right? Now this cost function, you evaluate several costs for different corresponding circuits. And ultimately, it helps you so the optimizer will do the optimization for you and tell you which will be a next better theta. So then with that, again, you will go back. So, okay, let's just see here. So now what this optimizer is going to do in this whole situation is, I have this as my cost function, right? So this is my expectation value, but obviously this is not the correct eigenvalue, which should be 0.39. So what the optimizer is going to do is, I will feed this value into it, and it will give me it will help me somehow figure out what is a better theta to start with. Or theta in this case is not theta, it's going to be the 3 parameters which we started with. So if you see here, this 0.917, 0.184, 0.708, what is a better combo of params? So that is what the optimizer will tell me. So once it gives me a new set of values, I will replace those values here and I will do the whole thing. I will calculate the expectation value, and once I have the expectation value, I will check, is it close to 0.39? I mean, ideally, I'm not checking if it's close to 0.39, because if I already know the answer, why am I trying to calculate it on a quantum computer? But rather, I will ask the optimizer again, is this value optimal? So if it is yes, it will stop. If it is no, it will give me a new value. And then I will go back and do that again. So this is the optimization loop in a VQE. Okay, so now I will define an overall expectation function where I'm doing the Z measurement, so, and then an X measurement, and I'm calculating the cost. So as you see, this is my cost function. Okay, and this function, this expectation function, is returning the cost. It's basically doing exactly what we were looking at before, and it's important that it is only simply a function of params, because that way I can easily feed it to some I can feed it to an optimizer. So let us first break off and create this function. Now, before you could use, there's this module which is the community package, Qiskit algorithms. It still exists. I mean, you can use it, but there are quite a few incompatibilities with the existing Qiskit, right? It's not fully up to date. So how do I change this to make my result? How do I change this to obtain my result? Now I don't know what to do. So it's actually simple here. So Kobela is an optimizer, right? It's not just in Qiskit algorithms. It's found in SciPy, and you have multiple options for say using a optimizer. Like there are so many classical optimizers available, and SciPy is one of the best packages you can use. So from what I'm going to do is from SciPy, I'm going to import minimize, because I want to minimize this function. So what I will do here is I'm just going to take off this whole line. So I have Kobila maxiter. So maxiter means how many, at what time do I want to stop? And tolerance is how good do I want my answer to be? And display parameter, basically at each iteration, do you keep wanting to see what is going on under the hood during the optimization? So that is what it is going to control. So I'm just going to backspace this whole thing. Now I have already imported the minimize function, so I'm just going to say from SciPy import minimize, and I'm going to feed expectation function params. Now I will say method equal to Kobila. I don't want to put a maxiter because I want the optimizer to choose that itself. So, but what I am going to input is tolerance, and say I want it to be 0.001, and let us say display, I don't know if this is the right parameter. Let us see if this works, else we will display equal to true. Let's just work with this and see what happens. Sorry about that. Let me remove this and see what happens. Okay, I fixed it down, so I'm just going to scroll down and see how I fixed it. Just put Kobela for now. I think maybe you should supply it via options. So let's try supplying it via options. I know what happened. It should be scipy.optimize. It's import minimize now. Okay. What do we do here? Yes, this is the correct line. Another thing here, it's very natural to like not know how to change something, or like to run into errors. Never feel like you don't know something just because you're running into an error. Always go refer the documentation, do a Google search, look at Stack Exchange. It doesn't matter. So like working around coming across these kind of bugs is very natural, and that is why I actually let it be here, so that I can show how I change it live. So now, for now, let's just go with this and see what the optimization looks like. Actually, I can pass the tolerance. It should be fine. See if it does display, else. Okay, so if it says it's an unexpected argument, then we want to remove it. So let's just see. So that the reason that happened is because there was some like during, so each optimization process can look different, because the optimizer also will make different choices at different points. So given that is the case, you obviously saw that I ran this twice. It was not once, right? The first time there it showed some error. And that's probably because it got stuck in some kind of local minimum. But when I ran it again, you see it actually converged. And this is like not a great convergence. It's 0.423, but it's much, much better than this 5.124 in terms of closeness with 0.39 that we originally started with, right? So this is a much better convergence point. So say I increase the tolerance even further. See, let's see what happens. It can take a much longer time to get optimized. You see here, it's actually strange that it got to 0.39 and then it came back to 0.4032, and it took 55 iterations. So say I reduce the tolerance a bit, and say I put max iter equal to or like some 40. What happens? Okay, so this is not a accepted argument, so let us remove it. Let us see if options is so options is an accepted argument, so this is how I should likely send it. So now it's working, right? So what is the returned value? So the returned value is this, which is not correct. So let us just, so since this is all classical, you can play around with this. You don't have to do it in a like very, like here it is okay to play around a little bit because it doesn't consume that much of your time and you don't lose as much resources. So I'm going to do it one last time. Let's see where it goes. Okay, it's returned 0.40 now, and I'm satisfied with this value because it's quite close to 0.39. So now Cobila isn't the only method available. If you hover over this, you see you have many options. Now the editor that I'm using is called VS Code. You can use Jupyter Notebook, but you see you have so many options for for what optimizer to choose. Now this is another thing that varies across like variational quantum algorithms. You can use any. Cobila is good in general, but if you're running on real quantum computers which have noisy systems, SLSQP and SPSA is good. SPSA is not here in this list, but SPSA also makes 2 evaluations per iteration, which means that it calculates an expectation function twice. So that will actually cause your, so if you pass 100 iterations, it will run for 200 iterations sometimes. So that's something to keep in mind. But generally, we tend to use SPSA a lot when we are running on real hardware. So now I'm just using some fake backend, and this is from, these are modules from Qiskit IBM runtime, right? So now, okay, now I have done this whole process manually. I have an idea of the answer. This is my answer from a simulator. Now this is always the next stage before running something on a real quantum computer. You try running it on a fake backend. What does this help you to do? So for running it on a real backend, there are going to be several things, right? You want to pick optimal qubits. Oh my God, we are almost out of time and we have a lot left to cover. So let me just finish this. So here, when you're running it on a quantum computer, let me, yeah, I want to show this. So, okay, this is like a picturized version of the variational quantum algorithm like workflow. But yeah, I'm not going to go into detail into that now. So if you look at the steps in a Qiskit pattern, the first is to map your problem, etc. And then you want to optimize it for target hardware. Now that's the second step. And that involves doing quantum circuit compilation or transpilation, which you can do via generate preset pass manager. So first I will initiate my backend, which I'm choosing fake Mumbai V2, and I'm creating a sampler which is using that backend. Which is using that backend. So now what do? You run now to get the expectation value. You are running it on the sampler. You're not running it. You're not running. Okay, yeah. So now this is, so sampler is one of the available primitives in Qiskit, and sampler usually returns count. So since I'm following the same procedure, I'm using sampler here. But ideally, for estimating expectation values, estimator primitives makes your life a little bit easier in some ways. We will see that in some time, but it's essentially the same thing, but now it is ready to run on a sampler. Okay, and the first step to do here is to create a pass manager, and this pass manager will transpile your circuit. So when I have this var circuit, now let us just do one step. say backend dot basis configuration dot basis. I try to print this. Dot audit. Okay, so now this is giving me all the details about this backend. Now keep in mind backend.configuration actually got deprecated. So this is working since it's for a fake this thing. It will work for real backends also. But for real backends, you can actually directly access them by saying backend.basisGate. So say if you're using something like IBM Torino, you can just say backend is equal to service dot backend of IBM Fez. And then if you write print backend dot basis gates, then it will actually directly give you this. Now this is what I was looking for. Now there is no U3 gate here, right? U3 is not in the basis. So if you directly try to run this, it will not run. So what you need to do is you need to transpile your circuit before running it on. So here in ZMesh TR, I am transpiling the circuit. Same thing for MEAS TR, I'm again transpiling it. So then you supply to the sampler fake, it will run the circuit for you. And you retrieve the counts and then you get the total counts and then you do this exact same thing which you did before in the previous thing, right? Now again, this is using Kobila from Qiskit algorithm. So we don't need to do it again because it already recognizes the minimize function. So I'm just going to directly use this now and say method equal to Kobila and supply tolerance. Let us go with 001 because it might take a lot of time if we put something too high. Now you see it's obviously running. So the main thing is that you start working with notebooks, you take the code, you start working with notebooks. Every time you see an error, first read the error and try to figure out what is causing that error. So like sometimes it will be very intuitive. It will say, I think you're missing a comma, or you need to put brackets in front of a pub if you are inputting a pub into an estimator or sampler. So simple errors like this you will be able to fix just by reading the error message. For more complicated ones, just look it up, or try making some changes, like put it in the web, like ask someone, ask on Stack Exchange. There are so many like ways you can get over that, but you will ultimately learn how to fix this only as we work hands on and get more experience with these notebooks. So that's my suggestion. Okay, so it ran and it terminated successfully, but it didn't give a great value, but it's not too bad. It's not something like 2 point something or 5 point something. But this is where the initial parameters that we pass make a lot of difference. So now let us do something let's do something interesting. What I'm going to do, so here we got this 0.406, right? Now the value of x corresponding to this 0.406, or specifically the value of params corresponding to 0.406 is this. So for fun, let us just try passing, instead of choosing our our parameters randomly, let us try passing. Okay. Let us try saying params equal to, and I paste this. Now let us see what happens if it so now since I'm passing a very good value, it should take lesser iterations to run, and it should hopefully converge to an even better minima. Let us see what happens. It's not guaranteed, but it's not guaranteed, but I would expect it to happen. So let us see what happens here. Maybe I should have reduced it. Okay. It increased. That's a bit disappointing, but oh no, it did decrease a bit. It was 0.6 before, if I was not mistaken. and this is closer to 0.39 than like 0.6 was. But yeah, so this is how, but and it actually only ran for 35 iterations, I think. But yeah, this is kind of the workflow. So you can also try changing the optimizer. So and see which one runs better. So for example, Nelder Mead also performs quite well. So you can pay. So these are called as hyperparameters of an optimizer, and this is one of the more bigger challenges of controlling, not just for quantum, like optimizers which run quantum subroutines, but just optimizers in general for any purpose. So that is something to keep in mind. Now, yeah, so this is the demonstration and workflow for how we use a VQE on a real, like say, on a fake backend. Now, it feels like a very, what to say, we solved the whole thing using just this, right? Where is it? How did we get that ideal 0.39 value? What we did was we ran it in the linear algebra module. Yeah, it was a bit after this, I think. Okay. No, I want to find the one before this. Yeah, so here when I ran this function, I already solved the minimum and the maximum eigenvalue. So this whole workflow was finding minimum. If you want to find maximum, it's very simple. You just negate the cost function. So if you put the negative of the cost function, it's going to maximize instead of minimize. So that's a simple thing to do. So I just put a minus in front of this whole thing, and then like I'm done. The whole, if I in this process, it will then look for the maximum eigenvalue and should get that 7 point something that was there. So now this whole thing was for a single qubit case. Now for a 2 qubit case, what do we need to do? Now we are almost at the end of our session time, but so let me try to kind of summarize what we need to do in a 2 qubit case, rather than like and then we can take some questions, and like if we have time we can go through further. But so this yeah, and going back to that point, if I was just able to use just that lean alg for say function to find the linear find the eigenvalues, why bother doing it on a quantum computer and taking all this pain, right? The reason is, now try using that lean alg function on a humongous matrix, say a matrix of size you know let's say 2 to the power 20 cross 2 to the power 20. Such a like even inputting such a matrix will be very challenging as data, like in your classical computer, right? So as we scale up further and further on 120 qubit systems, we are dealing with, or say a use case which is dealing with 120 qubits, you're looking at 2 to the power 120 cross 2 to the power 120 matrices for which you're trying to find the eigenvalue, which is huge, right? So in the bigger cases, it's much easier to like work, or it's more say rewarding to use a quantum computer than a small computer, and that kind of ties back into why we need to work with utility scale circuits and utility scale problems, why that is more relevant for using a quantum computer, because for the smaller number of qubits, classical is much more efficient. So let's just use classical there. Now coming back to this, so if I have, say instead of that, I want to calculate the expectation value in a bigger system, like say, sorry, if I have an operator L is equal to 2xx. So here xx is x tensor product x, and this is a 4 by 4 matrix, 4 cross 4 matrix. It's not, yeah, it's not like a small one, it's a 4 cross 4. And if I had three terms, say 2xxx, then it will be x tensor product x, or x cron x, and that would be 8 cross 8, not 6 cross 6 or something. It will be 8 cross 8, which is nothing but 2 to the power 3 cross 2 to the power 3. And here now what do we do? So here also we can use this linear algebra module to find the eigenvalues. It's not too complicated again. It's 2 minus 2 2 minus 2. So we know what should be the answer. The answer should be -2 in this case, because that's the lowest eigenvalue. The maximum will be +2. So again, now in this case, we have two like now we have 2 qubits, it's just not 1 qubit, right? Now for creating the like now for creating that general state or ansatz, instead of using Rx, Ry, Rz, let us use, we can use a combination of Ry, Rz and C naught, which is an entangling gate. So there are studies done on what kind of ansatz can be the most expressive for like, you know, representing a general state which covers every single you know, possible state. So for the 3 qubit case, we know that with some kind of alpha, beta, gamma value, or like some value to each of the parameters, we will be able to cover the whole you know, block sphere or the set of possible states that can be contained by 1 qubit, right? But for 2 qubits, it's not so simple. You can use Rx, Ry, Rz, but you will still not be covering some states which will get left out. So for covering those states, it is good if you introduce some kind of entanglement into the system by using C naught, by using Cx, Cz, some kind of entangling gate. So that is why, so this is called as so this is another type of ansatz, and this one uses Ry, Rz and C naught gates. So and another thing is, you don't just have them once, you repeat them multiple times so that you have more knobs to control. So by introducing more layers of the same ansatz and repeating them, you have more knobs to control, and because of that you kind of increase the possibility of the number of states, you expand the space, and you expand the possibilities of the states which exist, which may exist outside, say what you will get if you just have one layer. So now here we create a variational circuit with using you know, Rx, Ry, Ry, Rz and a C naught, and I have this for repeating for 3 extra layers. So here if you see, the input is params and depth. So if I pass say 3, then it will repeat it thrice. So let's just create an yeah, so now we have, this is what the circuit is looking like. So now if you write down the expectation function for ZZ, it's going to look a little bit different. So now our operator has 2 poly X matrices, right? So again, you have to convert them into Z form. So for finding the expectation, now I will have to convert each of the X into Z. So now this is just some mathematics which you can work out. So this is what it looks like. So the ZZ expectation value is nothing but number of 0 counts plus number of 1 counts plus minus 0 1 and minus 1 0. So I have this again. I'm just gonna say minimize method. Let's use Neldermead here. Okay, and this, let's run now this is running. I'm starting again with a random, you know, set of random initial state. And we have minus 1.7, which is actually pretty good. It's very close to minus 2, which is the ideal value here. So this was run on the simulator. Now let us try a fake backend. And for fake backend, you want to like transpile the circuit. Let us use optimization level 2 and not 1 or maybe even 3. No, let's go with 2 because I don't want it to take too long. So it's the same thing, but I'm just using optimization level 2 because I want the circuit to run a bit faster. Doesn't make much of a difference on the fake backend, but on a real backend, it will matter. Okay, again, now this got even better. I got to minus 1.8, which is much closer to minus 2 than minus 1.7 was. Now, yeah, so now as an exercise, you can also calculate it for something like 2xx plus 6iz. So the first term we already know how to calculate. So for the second term, you need a different circuit. So one thing to keep in mind is sometimes this L operator, like say in some chemistry like problems where you're dealing with spins of systems, you might see something like, say you might see something like the observer can look like Z1 plus Z2 plus Z1 Z2. Now, if just because it says Z1 plus Z2 doesn't mean that Z1 is isolated. That Z1 has a term after that, like which goes by identity. So each of these are uniform 4 by 4 matrices. So Z by itself will be a 2 by 2 matrix, right? So so that you have uniformity across all the matrices, the size of the matrices you need to expand or contract your like say observable operator by inserting identities. Now one more thing to keep in mind is we are just running it on a fake backend now, but if you work on a on a simulator, if you run it on a fake backend or a real backend, some things that can throw an error or cross problems is those systems will run for a fixed number of qubits, say 133, 156, 127. So you need to expand your observable, and it should match the layout of the circuit as well. So you need to insert identities accordingly, do whatever, but you need to expand or contract your um, observable accordingly. So that is another point to keep in mind. Now again, we used a sampler, but you can use an estimator as well. So that and like doing a more complex problem, I will leave it as assignments for you guys. So I'll finish my session there. Any questions? Okay, I see some questions. Uh,
Ma'am, I think the questions are from, there was one at, currently the, niche.
okay. Oh, I'm sorry. Like, so I wish someone had unmuted and told me. I don't know if the screen was visible properly. I hope everyone was able to see, right? Or was the
Screen was
text too
visible.
small or something?
They were only asking if we can have the, what do you say, the black and, instead of black background, they were looking at if we can get the uh,
I see.
light
Okay.
colored background. That was basically.
Sorry about that. Like I have my default one as black because light attracts bugs, right? So in a development environment, it's good to have. I like the night dark mode in my system, but I'm sorry I didn't see this request before. I could have turned it to light theme if I had seen it on time. So if somebody could have just unmuted and told me, sorry about that. Next time, please feel free to do so.
Yeah, there are, Annapurna ma'am, you can actually put this thing on the chat, or you
Yeah.
want to speak?
Yeah, I'm just trying to see. Okay, so design a noise aware framework. So this seems like a very, very specific question, so it will have a more specific answer. But to just answer it, okay, let me read out the question. Yeah, I'll share the demonstrated file, yes. Okay. Yeah, this question, let me first answer that. How to design a noise-aware VQE framework that guarantees chemical accuracy approximation of a Bravi-Kitev mapped molecular Hamiltonian using limited connectivity, shallow ansatz depth, minimized measurement cost, and probably non-trivial optimization landscape. That's a lot of demand, but to simply answer it, you go for any Hamiltonian, any molecular Hamiltonian. You take the Hamiltonian. The main requirement, especially for chemistry problems, is to know of a good educated guess that will serve as the ansatz for the problem. So once you pick an ansatz, you take the ansatz, create the generalized quantum state. So to make it noise aware, there are two optimizations you can do. The first would be to like really tweak your transpiler option such that the gate depth is low, and you are doing noise aware routing of the circuit, so that you, say for example, avoid noisy qubits or the like. And yeah, so the second thing would be limited connectivity, shallow ansatz depth. So that's again an ansatz optimization process. So like that is very problem dependent, depends on what ansatz you pick. Depending on what ansatz you pick, you can increase or decrease the connectivity. For real problems, like there is always a trade-off of how much depth you allow, or how many repetitions of the layers of ansatz you give, versus how many parameters you generate, and that causing the optimization to blow up. So say if I'm optimizing say 100 or 120 parameters, it's going to take forever, and it will not converge to a good value also. So in that sense, yeah, you choose a good ansatz, choose a suitable optimizer, and go for a suitable depth. There are several optimizations you can do on top of any variational quantum algorithm. You can explore those, and you can also enable error mitigation options via the estimator primitive. That will again cut down on the effect of noise on your expectation value estimation. So Air Simulator is not accessible in Jupyter Notebook. So I don't quite understand this question, but one remark I will make is that you can no longer access Air through the Qiskit module. So Qiskit Air is a separate package. Use the Qiskit Air package to access the Air Simulator. So that is how you can kind of try to work with it. Yeah, any testing frameworks to test quantum algorithms? So there are actually several. I would really, so like running it on fake backend itself is a form of testing it before running it on quantum hardware. So there is that. But aside from that, you have things like the NEAT tool. You have a separate library called as Benchpress, which is there in the Qiskit ecosystem. This Benchpress library really has a lot of toy circuits that are kind of based on several quantum algorithms that you can use for testing purposes, if that's the kind of test you want to do. So but if you are developing a quantum algorithm and you want to test it, the workflow would be to run, like, first develop it, run it on a simulator, then run it on a fake backend, then run it on real hardware, then scale it up, eventually introduce error mitigation options, etc. I am not sure what template matching optimization is, so I'm not sure I can answer that question. By the way, that comment I made on white like background attracting bugs, that's just a jovial one. It's more like, it's just if you have light switched on somewhere, it attracts moths and bugs, right? So you can have, anyway, I'm not going to explain the joke, but it was just a joke, so don't take it too seriously. Yeah, thank you for your attention. Any further questions? I'm just scrolling up to see. Okay, suggest any. Yeah, I think that's about the questions. There are a few I see, but maybe we can take them later. So, yeah.
The earlier questions are related to the previous talk.
Oh, I see. Okay.
So that part is, yeah. So thank you so much, madam, for your valuable time and for sparing the demonstrations. Actually, the notebooks will be shared. So please understand that when we are looking at that, it's an editor, and you need to install Jupyter Notebook to run those codes. And basically, you can execute them, and they are Python libraries. So that's what is basically Jupyter Notebook is to run Python codes. So basically, that's what you can look at. And once you install the software, then you can access the files that madam will share. So please try to understand that, and then you can take it forward. Right. So we'll thank ma'am for sparing the time one more hour with us in this schedule. And thank you so much, ma'am, for your valuable time. And the participants, we will conclude here. Tomorrow, we'll make an announcement regarding those who have missed their quiz exams. Okay, so please be patient till tomorrow, and we are planning to release the certificates by Monday, which will have a National Quantum Mission and IBM logo, the 8-bar logo they have approved. So we'll have that in this certification. So you will all be happy to receive that, right? Thank you so much. Thank you once again, Janani ma'am, and hopefully best wishes for your development works on Qiskit. And participants,
Thank you, sir.
tomorrow is the last day, so we'll look at some expert from either QNEO or from CDAC Q Inverse. We'll have a session, and we'll thank you so much, ma'am. Thank you, participants.
Thank you, sir. It's been a pleasure to be here.
Yes.
Thank you, everyone.
Thank you. Tomorrow we will meet at 3 o'clock for the last session. There'll be valedictory till 5:30, and we'll continue. Thank you.
Okay. Bye, everyone.
Bye.
We can 12.